we've really mostly been talking about collisions between identical objects, head-on collisions between identical objects, one at rest, and of course that's kind of a very small set of the interactions that are interesting in the world. So another thing to consider is interactions between objects that are really very different in mass. And so here's an object that's sort of massive. And here's an object that's not very massive. So what's going to happen if the bowling ball is initially at rest and we throw the ping pong ball at the bowling ball? Wasn't that a great... Well, that's an interesting question. The opposite is a very interesting question, and we do want to think about that. So this one... So let's assume that we're astronauts and we take this bowling ball and ping pong ball up into the space shuttle and just let them hang in the air so we don't have friction issues. Okay, because friction, if the bowling ball had wanted to move, it's interacting with the table and there is some friction there. So let's consider doing this in the space shuttle where we have a bowling ball floating in the air and we throw a ping pong ball at it and it bounces back. So what do we expect to see? What happens? So the question is, what happens to momentum and what happens to energy? So the first question is, let's think about momentum. And let's assume this is elastic. They certainly didn't stick together, so elastic sounds, or close to elastic. In fact, none of the collisions that we can manage between macroscopic objects is actually truly elastic. Because, think of, what evidence do you have that this is not completely elastic? No, the ball didn't slow down very much. Did you hear anything? You heard a sound. How do you hear a sound? Did that have to make the air move? It had to make the air move. It had to give some energy to the air, didn't it? So if you could hear it, some energy was lost to the air, and so that's not completely elastic, but we're going to assume it's pretty close. The kind of collisions that really can be completely elastic are usually between microscopic objects where, because the energy has to come at only certain amounts of energy can be transferred. Remember the Frank-Hertz experiment, you shoot electrons at the mercury atom. Almost nothing happens until the electron's energy gets high enough to excite one of the electronic levels of the mercury atom. That's inelastic, but up to that point, that collision was elastic. No energy could be transferred because there was no way to do it. Okay, so what do we expect for, so here's our system. Here's a bowling ball. Here's a ping pong ball. And here it is coming back. And let's say this is 2 grams, and that's, what do we say? We'll make it 5 kilograms because this is just going to be easy to do. And let's say it's going at 10 meters a second, which is actually high, but. And let's say it bounces back at a speed that's close enough to 10 meters per second that there's very little change. So it'll be a little smaller, but. So what's the momentum of the bowling ball after this collision? In outer space, in the space shuttle, everything's floating in the air. We throw the ping pong ball at the bowling ball. The ping pong ball bounces back. Yeah, so the momentum principle says P final is P initial. So we have 2 grams times 10 meters per second. So change it to kilograms. So 0.002 kilograms times 10 is 0.0200 kilogram meters per second, right? Maybe. And plus 0 for the bowling ball. And over here, now the ping pong ball has a momentum of minus 0.0200 kilogram meters per second. So the momentum of the bowling ball is 0.04 plus. Okay, so the bowling ball actually has larger magnitude of momentum than the ping pong ball does. That's what the momentum principle says. What about their speeds, though? Yeah, so let's see about speed. So the V final of the ping pong ball is going to be negative 0.0200 kilogram meters per second divided by 0.002. So we're going to get negative 1000 meters per second. What's the velocity of the bowling ball? Oh, we've got 0.0400 kilogram meters per second divided by 5 kilograms. So what's its velocity? 0.00800 meters per second, which is probably why you're not seeing it move. Yes. Well, it's the unknown in this equation, right? So we have plus P final of the bowling ball. And so we'll just solve for it. So we just solve for it and we get P final of the bowling ball is 0.0200 minus so we get so remember that signs count for momentum. We gotta pay attention to signs, right? So the bowling ball actually has more momentum than the ping pong ball, but it's going much slower. So, all right, we agree on that? Okay, so what can we say about energy? What's the deal with energy? So after the collision, we know what the momenta are. We know what the velocities are. What do we expect to see for kinetic energy? Now remember, this was elastic, nearly. So there are a number of ways to do it. You can think about the numbers we worked out. You can just think about the phenomenon, yeah. Well, we're in the space shuttle, and so we've got air because we're astronauts and we want to breathe. So, yes, we would hear a sound. But if we took it outside this, put on our spacesuits and we took it outside the space shuttle, where there was no air, and we threw the ping pong ball at the bowling ball, there would be no air to have energy transferred to it. So, no sound. Okay, so the most popular vote is for 4, which says that the kinetic energy of the bowling ball is going to be really teeny compared to the kinetic energy of the ping pong ball, mostly because it's moving really slowly. And we get this speed squared in the energy. So let's just figure it out just to make sure. That sounds right. But the final kinetic energy of the ping pong ball is a half times 0.002 kilograms times 10 meters per second squared, which looks like that's a 1, so it's about 100.1 joules. Does that sound right? What's the kinetic energy of the bowling ball? So we have a half times 5 kilograms times 0.008 meters per second squared, which comes out to 1.6 times 10 to the negative 4th joules. So it's about a factor of 1,000 less than the energy of the ping pong ball. So a lot of momentum gets transferred to the bowling ball, but very little kinetic energy. All right? Okay, so you ready for a hard problem? This is a standard physics textbook problem about a kind of a collision. It's something that actually can be done. So if you have, say, a wooden block at rest on a nearly frictionless surface, and you shoot a bullet into it, and the bullet actually sticks inside the block, but the block is free to move. So what are we going to predict about what happens to energy in this collision? Okay. So big majorities say that the final kinetic energy of the system is less than the initial kinetic energy of the system. And why do you suggest that? Inelastic, because they stuck together, didn't they? And in fact, what happened to some of that kinetic energy? Yeah, it's going to get really hot, isn't it? Yeah. So a lot of it really did go into heat. Okay. So we definitely expect it to be inelastic. So what's the energy equation for this collision that we'd use here? So okay, good. So you pick equation 3 because it's consistent with what you said in the previous question, right? If the internal energy changes, then we better include internal energy in this energy equation. And what about momentum? Does the momentum of the system change? No. Okay, good. So what's going to happen next time is this. We'll talk a little bit. So we've been dealing with basically one-dimensional collisions, head-on one-dimensional collisions. And you should look at the book about what you brought up, the bowling ball hitting the ping pong ball, because it's actually, the result is actually interesting. The ping pong ball goes really fast. We're going to talk next time a little bit about 2- and 3-dimensional collisions, which gets a lot more interesting in the Rutherford experiment. And then we're going to actually probably start angular momentum next time.